Dear students, in this video I will explain you about code generation, that is last phase of the compiler design as well as last part of your module 5. What are the requirements of a code generator? Let us discuss. First of all, what is the input which is given to the code generation phase? That is nothing but the output of previous phase. As we have discussed already, the previous phase of the code generation is either code optimizer or intermediate code. So let us consider a non-optimized code. So the input for the code generation is output of intermediate representation. So what are the different types of intermediate representation we can make use of? Either syntax tree or tree address code, etc. So it generates the output in the form of target program. So output of the code generator phase is in the form of a target program. This target program may make use of a high level language like C or assembly language. So for our convenience, let us consider this target program is in assembly language, that is which will make use of mnemonics like add, sub, mul, jump, etc. Now, the target program must preserve the semantic meaning of the source program. That is, when a statement is converted into target program language statement, it should have the same meaning as that of your source language. So that preservation of meaning must be there. Then another requirement is about quality. The target program must be of high quality. That is, it must take the effective use of available resources of the target machine. So the target code must have high quality itself. Then it must run efficiently. With respect to the running time, it must run efficiently. These are all the requirement of code generation. Now, very important topic in this particular chapter is what are the issues in the design of a code generator. Issues in the sense, what are the important measures that a programmer has to take to design a code generator. There are 5 important issues. First one, input to the code generator. From where the input has to be taken, how to take the input, etc. are the issues to be discussed. Second issue is about target program. What is the language of the target program? How exactly the code has to be converted into a machine language? Then third issue is about instruction selection. When a particular source program statement is converted to a target language statement, how the instruction has to be written. That is, instruction selection depends upon the architecture of the machine. Then fourth issue, register allocation. How to make use of the available resources like register R0, R1, general purpose register, or sometimes special purpose registers like link register, stack register, etc. So how to allocate the register for the efficient execution of the program. That is also an important issue. And finally, evaluation order. When a source language statement is written, then how exactly to evaluate this, in which order, top down or bottom up, something like that. Or if you consider a mathematical expression, then whether associativity is from left to right, or how exactly the precedence has to be considered, etc., comes under evaluation order. So these are the main issues of code generator. So students, please consider this as very important topic. You can go through with you question paper. In each and every question paper you have a question like explain issues in the design of the code generator for either for 8 marks or 10 marks. Once you understood the concept, you can easily write the answer. Now let us see one by one. First issue, input to the code generator. So as I have told you already, the input for the code generation generator is taken from intermediate representation. That is, with the symbol table information to find out runtime addresses of the program. So I think you know about this symbol table. Symbol table is a table which contains all the information about the variables or the constants used in the program. Symbol table is constructed during the lexical analysis and it is used in the remaining phases of the compiler design. That is, from syntax analysis to code generator, we are making use of the symbol table which is constructed during lexical analysis, which may have two columns. First column is like name of the variables which are used in the program, and second column is about the properties like data type, size, etc. Okay, that is the symbol table. So code generator takes the input from the intermediate representation with the symbol table information. If the intermediate representation will make use of some temporary variables like T1 or T2 or some register R0, R1, etc., then that representation with the symbol table is considered as input for the code generator. So the choices for the AR may include which is the intermediate representation the code generation should consider. There are different possibilities or the choices. What are those? First one is 3-address representation. So in the previous topic we have discussed different 3-address representation like quadruples. Quadruple in the sense there are 4 fields like operator, argument 1, argument 2 and result. So either quadruple form or triple form where indexes are used, or indirect triples where the pointers to triples are used. So input can be of the form 3-address code. That is the first choice. Then second choice is about virtual machine representation such as byte codes and stack machine code. You can see this one in case of our Java virtual machine. Suppose the source language is in Java, then byte codes can be considered as input for the code generator. Linear representations like postfix notations. We have some notations like postfix, prefix, infix, etc. So the representation like postfix can also be used as intermediate representation. And last one is about graphical representations, which we have discussed in the previous topic, either syntax tree or directed acyclic graph tag. So these are all the different possibilities for the inputs which can be considered as input for the code generator, that is output of the intermediate code and input for the code generator. This is about the first issue, input to the code generator. So input is nothing but intermediate representation which may take different forms like 3-address code, byte codes, or linear representation like postfix notation, or graphical representation like trees and tags. And more commonly, every code generator will make use of either syntax tree or tag or 3-address code as the input for the code generator. So please remember the first one 3-address code or the last one syntax tree or tag can be considered as input for the code generator. This is about the first issue. So what is the second issue? It is about target program. Target program in the sense the language which is used to write the machine code. So most common target machine architectures. So here this particular issue depends upon the architecture of the computer we are using. So more common architectures are either RISC or CISC or stack based machine. Let us see one by one. RISC you have already studied in the previous semester about RISC and CISC. I think in CO you have studied. It is nothing but it is an abbreviation for reduced instruction set computer. And CISC is nothing but complex instruction set computer. And last one is about stack based machine which will make use of stack concept like push and pop operation. Let's see one by one. First, let us learn the difference between RISC and CISC. So RISC has many register and CISC has lesser number of registers. Then RISC will make use of 3-address instruction and CISC will make use of 2-address instruction. It is simple compared to 2-address instruction. Then RISC will make use of simple addressing modes like direct addressing or immediate addressing. Okay, whereas CISC will make use of variety of addressing modes like indirect addressing or indexed addressing, etc. Then RISC contains relatively simple instruction set, whereas CISC contains variable length instructions and instructions with the side effect. So Target program may make use of either RISC or CISC depending upon the architecture used. Then what about stack-based machine? As we all know, stack is nothing but which is the data structure which will make use of push and pop operation. The item which is pushed on the stack can be removed at the end. So push the operands and perform operation on top of the stack. Whenever we use stack concept, the operation which will be done using top of the stack. So push the operands first. Then to achieve high performance, top of the stack is typically kept in register. Students, do you know what is the reason behind this? Why top of the stack is typically kept in register? That is regarding memory access time. Always registers are nearer to the CPU so that memory access time will be less. That's why to achieve high performance, top of the stack is always kept in registers. According to the memory hierarchy, the speed with which they execute if the operands are in registers will be more. That is the reason. Then stack-based architectures are revived with the introduction to Java Virtual Machine, which is the software interpreter. Java Virtual Machine is the interpreter. Line by line execution takes place, and the intermediate result, which is called as Java bytecodes, and the intermediate language produced by the Java compiler. So stack-based architecture we can see in Java virtual machines, as well as one more compiler called as just-in-time compiler we studied in module 3, first part of our compiler design. They translate bytecodes during runtime to the native hardware instruction set of the target machine. Directly, bytecodes can be converted into native hardware instruction set without any intermediate program. Then another approach to improve the Java performance is to build a compiler that compiles directly into the machine instructions of the target machine. As we have discussed earlier, there is no intermediate code, bypassing the Java bytecodes entirely. This is about a stack-based machine. So this is all about the second issue, that is the target program. Now coming then target program can be one of the following. Students, here just we will discuss in brief. You will study about these four different concepts in module 1, that is system software part. SIC and SIC architecture or machine dependent and machine independent architecture. In brief, I will explain for you. Target program can be of absolute machine language program. So absolute machine language program, in the sense it can be placed in a fixed memory location and immediately executed. We can't change the memory address from where it is placed. So fixed memory location and immediately executed. Programs can be compiled and executed quickly. Okay, that is called as absolute machine language program. Then second target program can be relocatable machine language program, exactly opposite to absolute. It can be relocatable. Once the program is located or loaded into the memory for execution, we can change the memory address. It allows subprograms to be compiled separately. Now one more thing is there, we can divide the program into many simple programs or subprograms, and they can be compiled separately. So after compilation, they will have the result. No, so those results can be combined with the help of a special software called as linker. Set of relocatable object modules can be linked together, as I told you, with the help of linker. So the different results obtained from different subprograms can be linked or combined and then loaded for execution by linking loader. So linking loader is about it is the concept which is discussed in the second module of your syllabus. If it does not handle relocation automatically, the compiler must provide explicit relocation information to the loader to link the separately compiled program modules. Last choice is assembly language program. It is the process of code generation which somewhat makes the process easier. We can generate symbolic instruction and use the macro facilities of the assembler to help generate the code. So give more importance for this as we are using this assembly language program as the target program. Third issue is instruction selection. So how to select the instruction? There are different factors we have to consider. First one is level of IR. What do you mean by level of IR? Can be high level IR or low level IR. High level IR is nearer to the source language program, so consider it as syntax tree. Low level IR nearer to the target program, so we can consider it as tree address code. Then another factor is nature of instruction set architecture, whether we are using CISC or RISC or stack based architecture. That also plays an important role in the instruction selection. Then another factor is the quality of the generated code. So whether it is of high quality or low quality or average quality. Then for example, consider this instruction x is equal to y plus z. So target program can be written as like this. This is the comment. First what we have to do, we will consider tree address instruction or two address instruction like this. First LD for load register R0 with the contents of y. Now R0 contains y. Now, each and every operation takes place in the accumulator, isn't it? So, add R0, comma Z. This three address instruction performs addition. How exactly it performs? R0 is having the value of Y and Z is there in the accumulator itself. So, accumulator adds the contents of R0 with the contents of Z. So, Y plus Z can be added and result will be stored in R0. See here R0 is equal to R0 plus Z. And then what is the storage location where we have to store the result? In X. So, store instruction X with the R0. Contents of R0 is loaded into register. Not register to the memory location X. So for this instruction, we need these three machine instructions. We are using mnemonic assembly language instruction. Just an example. Another example, consider this instruction A is equal to B plus C and D is equal to A plus E. This is translated into this 6 instruction. Observe carefully. Now, similar to our previous example, first load R0 with B, okay, B, then add B with the contents of C in the accumulator, store the result in A. Since they are executed one by one, sequential execution takes place. Load the register R0 with A, okay, for this one now. Now this is over. B plus C are added and they are stored in A. Then A plus E, you have to get the value of A into one register and then add the contents of E in accumulator and finally store. What we can observe is fourth statement is redundant. Which is the fourth statement? This load instruction is the fourth statement. Why it is redundant? See, according to this, R0 is having the contents of A. Right now, so it is already having R0 is already having A, then why we have to write this load instruction? So it is redundant. So such redundant instructions will be removed during the phase of code optimization itself. For another example, you see A is equal to A plus 1 can be implemented like this. Okay. So how? First load R0 with A, then add 1 integer 1 to the contents of R0, that is R0 is equal to R0 plus 1, then store again in A. Okay. So here suppose if the architecture supports this instruction INCA means increment A, just by using a single instruction you can perform this A is equal to A plus 1. These are all the modifications which can be done during the phase of code generation or code optimization with the help of architecture. That is, instruction selection is important. How it is important and why it is important, you can go through this example. So single instruction can be used if the architecture supports this. Otherwise, the instruction must be used. Here, this for statement can be removed because it is a redundant instruction. Fourth issue, register allocation means allocating the register to execute any operation. Registers are like general purpose register or special purpose registers. Use of register is divided into two sub problems. They are nothing but register allocation and register assignment. Okay, looks similar, slight difference. What is register allocation? First we select the variables that will reside in register at each point in the program. First consider variable and then consider the register. Register assignment is just vice versa. We pick a specific register first and then decide what variable will reside in. So that is the difference. First variable, select the variables and then decide register. Here pick the register first and then decide which variable will reside in. Okay, so these are the two concepts under register allocation. Last one is evaluation order. We have studied the evaluation order in a dependency graph as well as a annotated parse tree. So order in which computations are performed can affect the efficiency of the target code. They should perform the operations or computations in a particular order, then only we will get the proper result. Otherwise the result obtained will be wrong. So order of execution, order of computation can affect the efficiency of the target code. Some computation order require fewer register, lesser number of register to hold the intermediate result than others. So computation orders are also dependent upon the number of registers. That is, this fifth step is directly related to the previous step, that is register allocation. Then picking a best order in general case is difficult. However, the decision on this evaluation order in general is difficult. So each and every problem is different from one another and is had got its own properties. We cannot write an algorithm for picking up a best order for execution of an operation. So this is all about issues in the code generation. Now, a small discussion about target language. Let us define one target machine model, abstract model, how it looked like. So, let us consider a model which contains 3-address machine. Okay, 3 address, all instructions are of 3 address with load and store operations, with computation operation like addition, subtraction, etc., jump operations and conditional jump operation. So it is a byte addressable machine with n general purpose registers R0, R1, R2 up to Rn minus 1. This is the target machine model or the abstract model for the discussion. Load operation can take this form: load, destination, command. This is the format and this is the example. Already we used this load store instruction in the previous example, so easy to understand now. A has to be loaded into register R0. Store operation, this is the syntax, destination and source. Contents of R0 will be stored in A, memory location A. For computation operation, op, destination, source 1, source 2. Consider this: sub is the operation, destination is the n, R2 minus R3. So n is equal to R2 minus R3 can be written as sub n is the destination where we have to store the result, R2 is the first operand and R3 is the second operand. So this is the format. Unconditional jump, BR for branch, L for label, branch to label. Conditional jump, condition, that is branch on condition R, L. Consider the example BLTZ branch less than 0 R0, L. Meaning is, if the contents of R0 are less than 0, then go to label L. Branch if and only if contents of R0 is less than 0. In all this instruction, memory location can be specified by, how to specify the memory location? With the help of direct addressing or index addressing or register index addressing or immediate addressing. Students, about all those addressing format you will study in module 1, SIC and SIC bar architecture. I think you have some idea about addressing, already studied in computer organization concept. Still, once again, you will study in the first module. This is last topic, which is there for discussion. Program and instruction cost. What is the cost with respect to length of compilation time? That means how much time is required to execute a particular instruction, as well as size. What is the size required to store that particular program, then running time, as well as power consumption of the target program. So program cost or the instruction cost depend upon all those things. We will take the cost of an instruction to be 1, that is cost is 1 plus the cost associated with the addressing modes of the operands. Okay, so every instruction has got cost 1 plus additional addressing modes. Now if the addressing modes are involving only registers, then they have 0 additional cost. So their cost will be just 1, that is instruction cost. No addressing, only they are involving only registers, so 0 additional cost. But the instructions which are involving a memory location or constant, then they have additional cost of 1, because such operands have to be stored in the words of the following instruction. Okay, so if the operand is stored in the memory location, we have to bring that operand into the CPU for execution, and then once again we have to store the operand in the memory location. That's why we need 1 additional cost. Some examples, let us discuss in the next slide. Consider the instruction LD R0, R1. LD for load R0, R1. See here we are using only registers. There is no addressing. So what is the cost of this instruction? It is just 1, because no additional memory words are required. Okay, got it? No. Cost of this instruction is just 1, because it is using only registers and no additional memory words. Clear? Then second instruction, see here, load R0, M, where M is the memory location. Loads the contents of the memory location M into register R0. What is the cost? Cost for this instruction itself plus 1 for this memory operand. So total cost is 2, because of the existence of memory location. Okay, this is just 1 because of only the instruction cost. The cost of this instruction is 2, because 1 is for instruction and 1 is for memory location. Now consider the third one. Cost is 3. Can you observe why cost is 3? 1 for instruction, another one for contents of the register index addressing, and one more is for immediate addressing. Here just star indicates immediate addressing. So immediate addressing is there. Register indirect, see, if you write just register or not, this is direct register addressing. Then if you have parenthesis like this, then it is register indirect addressing. So 1 for instruction, 1 for register indirect, and 1 for this immediate value. So the meaning is given over here. That means load into register R1. Okay, load to register R1. This one, what is this? Contents of contents of 100 plus contents of R2, and don't be get confused now or don't worry about this and all. We'll discuss in module 1 addressing different types of addressing and all. So this is about code generation issues in the code generation, as well as we reach the end of module 5. Then students, after this we have just reached the end of compiler design part. Um that is module 3, module 4 and module 5. Module 3 is about introduction to the compiler as well as lexical analysis. Module 4 is about top down and bottom up parsing, and module 5 is about intermediate code generation and code generation. That is the end of compiler design part. Thank you. Happy learning.